It's my pleasure to introduce this last talk of the day for the courageous people that are still here. And this talk is given by Franklin Okoli. Franklin was a PhD, formal PhD, CAMI PhD student. He did his PhD at the LATIM at Brest in collaboration with Liam. And today he will present the talk regarding rapidly exploring random tree RT for creating non-planar VMAT treatment planning. So Franklin, it's up to you if you are here.
Good evening, everyone. My name is Franklin Okoli. I was a PhD student at LATIM Brest, and today I will be presenting one of the parts of my work that was one of the studies. This is one of the studies we did during my thesis, which is titled a sampling-based approach for non-coplanar VMAT using the RT star. So this thesis was carried out in LATIM Brest in collaboration with Liam. So I will start by just giving a general knowledge about cancer, and then I will then go to talk about the approach itself, and then I'll just give a final slide about my experiences in LABEX CAMI. So generally, cancer is a very leading cause of premature deaths today. About 2 million people who are dying in the world every year, in Europe every year due to this. So we have about 255,000 cases in France. So on this image, we have the map. We are seeing the cancer incidents all over the world, and we can see that it's a global problem. And countries where we have more red color have more incidents. So there are many ways that we can treat cancer, like everyone knows. We can use cancer surgery, where we try to remove the tumor by the surgeon, or we can use targeted therapy, where we try to target specific cells in the body and try to treat them while avoiding other normal cells around. The one that we focused on was radiotherapy, which is another modality that uses radiation to treat cancer. It's external radiotherapy that I was working on mostly. There's also other modalities like chemotherapy, which is infusing some chemicals in the patient to try to kill those cancers. And there's also hormonal therapy as well. These are all the different modalities. So generally, in treatment planning, the steps are like this. You start with the 3D imaging. At the first step, you take the image of the patient, then you do the segmentation, and then the clinician prescribes the dose at the third step. And then when you take the prescription from the clinician, and then you do treatment planning, and then you deliver the treatment at the treatment delivery stage. So our work is trying to change from coplanar VMAT, which we see in this image, to non-coplanar VMAT. So in coplanar VMAT, you have a patient who is on the bed, and we are trying to deliver radiation to this patient. So the gantry, which is the machine that you see that is turning around the patient, is moving only in one single plane, but it limits our ability to reach different parts of the tumor that are in the patient. So we would like to be able to reach more parts of the tumor, to be able to avoid the organs at risk. So that's why non-coplanar VMAT is much more the direction that everyone is going towards now. So in non-coplanar VMAT, you have much more large-scale problems. So you are able to reach different parts of the tumor and try to avoid the normal tissue, so you can make more complex trajectories around the patient to do this. So you have better organ at risk sparing. Problem that you have big problems because you have a lot of candidates possibilities to select the beam orientations. So in order to reduce the problem is to how to select the best solutions from this in order to move around the patient and deliver this beam treatment. So in the non-coplanar VMAT, there are different state-of-the-art methods like the manual methods, there's the beam IV methods, and there's other methods that depend on beam angle selection. For us, what we identified during our studies in the state-of-the-art is the risk of collisions were not well studied. There's a large space of solutions, so usually people limit the space of solutions that they sample. They just sample a small size of the solution space. And then there's also constraints with the machine that usually people don't consider during beam selection. And then the last part is the one that we will talk about today, where you insert unoptimized beam orientation after the beam selection part. So for our cases, generally, we propose the methodology for determining collision pre-orientations, and then we propose a beam angle selection algorithm that was based on simulated annealing. And the last part is what we will talk about today, the part for creating trajectories for non-complanar VMAT. So the state of the art for sampling approaches is not very large. In fact, we found one approach which is called MCTS by Dong. So he's trying to create a set of nodes that we use for the treatment using a Monte Carlo tree search. But the problem is that he doesn't consider the machine constraints, and he's only using the angular properties of the workspace to select the beams. He doesn't really consider the dosimetric properties of the beams itself. So what we wanted to do was to find a way to simultaneously select a beamer trajectory and at the same time evaluate the dosimetric contribution of that trajectory simultaneously during the trajectory selection part. So we wanted also to consider the machine parameters during the trajectory selection. And to do this, we found that RRT star was a good idea because of its ability to handle large dimension problems. So it enables us to start from a start node and then try to sample the space, and at each space we try to navigate towards the next node. So RRT is used usually in robotic trajectory planning or in robotic control, or usually in control of systems. But it's probabilistic, so you start to sample at random to try to attain it at a goal. I don't know if I can. The proposed algorithm is like this. So we start with some input beam orientations. We create a graph from this beam orientation to the second stage. Then at each stage, we select a node from this graph, and then we try to steer to a certain neighbor node, to the node that we selected on the graph. So at each stage that we try to, at least after the steering part, we compute the cost function. The cost function that we use now is not the distance parameter, like the Euclidean distance between two nodes. The cost function we use is the dosimetric objective function. But this is a modification that we have made, and then this will help us to know if the new node that we have has a lower cost than the neighbor node that is already existing on the tree, and this is what we use to build up the tree. And then we have a stopping condition that is based on the number of iterations or that we fix. And at the end of the iterations, we run a depth first search, and from this we get the trajectory. So here I just show relationship we use to select the initial node because it's very important. Here we're using the first order estimate of the objective function. Essentially, this equation that we have here tells us that the initial node that we select is the node that will cause us to reduce the cost function the most among all the possible nodes that we can use to do this beam selection. And we use a fixed number of iterations for the stopping condition. So here we are showing what the algorithm looks like when it's proceeding. It's sampling nodes from the root node. It's sampling the space and builds up these nodes, and then at the end we'll have a tree that looks like this. And this tree is what the tree looks like, and then we will run the depth first search up from the terminal node to the root node to find the best trajectory on this tree. Here I talk about the modifications we made to the classical RRT style algorithm, like changing the steering function, changing the evaluation of the cost function from the evaluation of the Euclidean distance, for example, between two nodes, to the evaluation of the dosimetric objective. A very important part here is that we do not have any defined goal in this algorithm. So we want our agent to navigate the space without any goal in mind. We just tell him to navigate and find the best solution on this space. So our style helps us to be able to propose, to define this criteria. So some of the results we had is that we compared it to one of the algorithms that we proposed also in the thesis that is based on simulated annealing, and we saw that the RRT star was not better than that simulated annealing in terms of dosimetric property, but it was better than the classical greedy algorithm that we see on figure A. Is a classical greedy algorithm that is then figure C is the RRT star. So dosimetrically it is better, but compared to the simulated annealing method that we proposed, it is not better. So we also saw that, for example, for the DV19 case, we had reductions in the mean dose to the core by 40% and reductions to the body by 19% when we are using the RRT star method compared to the greedy method. But compared to the simulated annealing method, we're not better in terms of the results. For the prostate case, we also saw the same trend in terms of that we have a better result compared to the classical grading method, but it's not better than the simulated method that we proposed previously. I will not dwell too much on the DVHs, so I will not bore everyone. What is interesting here is that this study showed us that there is a trade-off that we can have between getting a very high-quality trajectory and getting a very good dosimetry in the case. On the left side, we see the non-compliant simulated method that is used, and on the right side, we see that the RRT star method is used. Dosimetrically, the one on the left side, the figure A, is better. But if we look at the trajectory that we compare, we see that the RRT star method has a much better trajectory in terms of the bending energy, which is the BE and the GBE. These are parameters we calculated used to compare the trajectory. We calculate parameters to compare the trajectories to see which trajectory has more curves, which trajectory has makes more worse movements around the patient. Movements around the patient is meaning like trajectories that are not naturally related. You know, if you have one node at one point and one super from the other, those two parameters help us to compare those trajectories, and we see that the RRT star method has a better trajectory compared to the classical simulated method that we have proposed. So from our study, we had some conclusions. We saw that when we add control points that was done in the state of the art, in the great pound quality, we were able to avoid this two-step approach that we found in beam selection methods. So we saw an improved dosimetry when we compared it to the greedy method, but an inferior dosimetry when we compared it to non-coplanar simulated method that we had proposed. But we had an improved trajectory compared to all the other methods that we saw. So our conclusion was that there is a trade-off to be had between treatment plan quality and the trajectory that we will use, the quality of trajectory that we will use to deliver this treatment plan. So some of my experiences from LabICAMEX that are very important for me was the ability to participate in local and international conferences. For example, I was able to participate in ICCR in Canada in 2019, and also the ability to meet every year in the LabEx CAMI days is also very important because, first of all, it helps me as a PhD student to know what everyone is doing and have another perspective with respect to my work. It's a very important way to see what every other person is doing. It also helped me in my professional career. I've worked on projects that are quite similar, but not in the same field. For example, I've worked on projects that use optimization for power grids. In that way, we are trying to optimize how we do the load, how we share the load between the different nodes on the power grid, and the same techniques are applied. I've also worked on projects that are linked with portfolio management in finance. So in portfolio management, you have a set of what you call maybe funds in your portfolio, and you want to optimize how much of them you want to hold in your portfolio. So with the same techniques in optimization, I was able to apply them in those projects as well. And also from LabEx CAMI, I was able to learn how to make presentations, given the opportunity to make presentations in front of a large audience. For example, in Brest in 2019, yes. And software development as well. During the PhD, you are able to develop software during this time, and then you gain research skills as well. So thank you for listening. I will be able to answer questions if there is any.
Thank you, Franklin, for the presentation. You have a question from Jérôme.
Okay.
Asking, Jérôme, I think we have time if you want to ask it, make it more interactive if you want.
Okay, thank you, Franklin, for this nice presentation. I just want to know if your method can be generalized to other kind of radiative therapy. I am thinking of proton therapy in particular.
Yes, it's possible to use this in other methods like proton therapy. In fact, it's quite agnostic to the final because proton therapy is quite similar to external beam therapy, because in proton therapy, what is different is that the radiation source is not exactly using electronic beams like what we have in the VMAT therapy. So what is different from the two methodologies are not much. I think that this can be applied as well.
Thank you.
Okay.
So I'm looking to YouTube. There is no question arriving. I have some questions. So the first one is: do you know what's the future of this work within the LATIM? What's the next? What are the next steps of this work?
Okay, currently we have someone who is working as well on similar projects to take it further. As far as I know, in LATIM we have to take the project to the phantom level, to try to do some clinical tests on the phantom, for example. But this will be from next year, when, from what I heard from the director, when we will decommission one of the radiotherapy machines, and then we can have the freedom to use that decommissioned machine as a test bench for some of these algorithms that we have. So the idea is to move them from being simulated, from simulated environments to the machine, the real machine in the CR breast. So next year they will decommission a machine, and from what I heard, we can use it in LATIM for this.
So a classical question that we ask: if you have to make again this project from scratch, are you going to choose the same tools, RRT? What about genetic algorithm, deep learning, new IDEA?
If I had to choose, because I really did spend a lot of time thinking about this, which algorithm to choose. It was not an easy decision. Genetic algorithm, it's not properly adapted for this because sometimes it's not properly adapted for this problem. In fact, RRT provided quite a natural way to model the problem. So deep learning, because the process for non-coplanar VMAT, the problem is that a lot of things can be quite random. If you try to learn something that is random, you could probably learn noise, So the choice of RRT provides quite a natural way to, while you are sampling the space quite randomly, because you have a fixed node that is the origin of everywhere, you have a sort of anchor in it. With deep learning, you could learn noise. You cannot repeat some of these simulations. So it's important that the model is able to model this.
Thank you. Last question. You didn't say what's your current situation, because you finished the PhD and now.
Yeah. Since 1 year now, I've been working in a financial company. It's called Lifeware. So since 1 year now, I work as a software engineer there, and we develop software that is used in life assurance. So we manage client portfolios, and it's mostly software development.
Okay, so if there is no more questions, so we can conclude this talk and give back the talk to Jocelyne to conclude the day. Thank you.
Thank you very much. Thank you, Franklin. Thank you, Nabil.